Welcome to This Explainer. Today, we're diving into the absolute fundamental language of machines, algorithms, and flowcharts. How do we take massive, complex, real-world problems and translate them into a language that a totally logic-driven machine can execute flawlessly? Think about this for a second. How exactly does a washing machine know how to wash your clothes? It doesn't have a brain, right? It doesn't possess human intuition, and it definitely doesn't just wake up and decide to be helpful on laundry day. Yet you press one button, and it perfectly executes this highly complex sequence of soaking, washing, rinsing, and spinning. It is entirely powered by an invisible logic that we pretty much take for granted every single day. Well, the secret is that it follows an explicitly programmed path of action. Every single machine out there, whether we're talking about a cutting-edge AI system or just a standard kitchen appliance, literally goes through exact, carefully engineered steps just to accomplish one specific task. Okay, let's dive into this. The formal term for these programmed steps, it's an algorithm. Simply put, an algorithm is just a logical, step-by-step method or procedure used for solving an identified problem. Whenever you're building a program, developing this algorithm is absolutely crucial. It's your very first step, kind of like the raw recipe for your solution. But what does an algorithm actually entail under the hood? At its core, it includes calculations, reasoning, and data processing. You're basically taking a main objective, specifying exactly what the machine needs to do, and then feeding it the precise logical reasoning it needs to process the data. Now, these algorithms can be presented in a few different ways. You can use natural language, you can write pseudocode, or you can use visual flowcharts. To make this super concrete, let's take a universally understood human task, making instant noodles. The algorithm here is incredibly simple. Step 1, boil water. Step 2, add the noodles. Step 3, add the flavor packet. Step 4, eat. We took the main goal and broke it down into sequential, highly actionable tasks. Now, I know some of you might be looking at that sequence and thinking, wait a minute, actually, I add the flavor packet before the noodles. And hey, that's totally fine. In programming, there can definitely be multiple approaches to the exact same problem, differing in the number of subtasks or the methods used to solve them. But here is the golden rule of computational logic. The best algorithm is always the one that is the simplest and the most efficient. Out of all the possible paths you could take, the most direct one is the one you want for sure. So, the crucial point here is the massive difference in how humans and computers process all this logic. Computers, they eat raw numbers and text for breakfast. They process it with absolute ease. Us humans, not so much. We often need visual representations to really grasp information quickly and communicate it effectively. Reading a massive wall of text detailing a 100-step process is just confusing for us. And this is exactly where we transition from a text-based natural language algorithm to a highly visual one. And that brings us to the flowchart. The flowchart is literally the ultimate visual blueprint. It's the graphical or pictorial representation of an algorithm. By utilizing different symbols, specific shapes, and directional arrows, we can map out a process or a program in a way that completely bridges the communication gap between human understanding and machine execution. And this brilliantly illustrates exactly what we're talking about. The goal here is simple. Find out if X or Y is the greater number. When visualizing this, imagine a diamond shape right in the middle of the process. That diamond is a decision point. The machine takes the inputs, reaches that diamond, and asks a purely logical question. Is X greater than Y? Based on its reasoning, the path literally splits off into either a no route or a yes route. Deconstructing this process step by step really cements how it works. First, we start. Next, we input our variables, X and Y. Then we hit our logic gate, if X is greater than Y. Depending entirely on the answer to that specific question, it outputs the correct calculation. And finally, it stops. You can literally trace how raw data moves through a logical question to reach a final definitive output. It's like a giant puzzle coming together. To really lock this in, let's compare two approaches for doing something practical, like converting Fahrenheit to Celsius. A written, natural language algorithm relies entirely on text-based steps to read the temperature and calculate the formula. But when that exact same logic is mapped out into a flowchart, the visual shapes and downward arrows instantly give you this intuitive sense of how the process flows from top to bottom. Let's move to how this builds a universal language. Flowcharts use specific, standard graphics. Ovals, they always signify the start or end of a program. Parallelograms always represent an input or an output, like, say, reading the temperature. And rectangles always represent a process, like the actual mathematical calculation itself. Because these shapes are totally standardized, anyone looking at them can instantly recognize what kind of action is happening, honestly, without even reading the text inside. So what is the major takeaway from the whole shebang? Whether you're mapping out how to make a quick bowl of instant noodles, calculating temperature conversions, or programming the next real game changer in software, computational logic is really all about one thing: breaking massive goals down into bite-sized, sequential tasks. You specify your main objective, and then you just build a step-by-step framework to achieve it. Before we wrap up, I want to leave you with a bit of a provocative challenge, straight from our source material. Now that you understand the mechanics of algorithms, decision trees, and those standard flowchart shapes we talked about, try to think computationally about a really simple, everyday game. If you had to map it out, what would the flowchart for a game of rock, paper, scissors actually look like? Think about what the inputs would be, exactly where those decision diamonds would sit, and how the outputs would finally declare a winner. It is a fantastic way to test out your new problem-solving framework. Keep thinking logically, and thanks so much for exploring the logic of machines with me today.